Welcome everybody to our first informal paper discussion TWed, and we're very thankful for Abraham Sanders to lead us off. As we've been socializing this term, we're integrating Tomek's group's paper discussion format with our TWeds, so we're kind of interlacing. We'll have our next scheduled paper talk is Danielle Villa leading us in decomposing that paper about DeepSeek R1 paper in a couple of weeks. And then we've got some other goodies, and there's still some slots available this term if you want to get some opportunities to present. And without further ado, Abraham, take it away. Thank you very much.
Thanks. I think there's anyone online right now. I'll just double check that they can hear me if there is. Anyone else online?
I don't, but that's fine. Okay. I started it up there. Okay.
So welcome to our first combined reading group, our language and cognition lab, combined with the TWed series. So this would be continuing our reading group. This would be the 94th NLP related presentation. Come quite a long way since 2021 when we started it. This is the first combined presentation with TWed, so that's exciting. We have a campaign on the right and a party. Today we'll be talking about a paper which came out this past year called Training Large Language Models to Reason in a Continuous Latent Space. And this paper is by researchers at Facebook or FAIR at Meta, and also in collaboration with the UCC.
And what is FAIR? I mean, I know what Meta is, but I don't know what FAIR is.
Facebook AI Research.
Oh, okay, got it.
So it was called FAIR before Facebook became Meta, so they just sort of carried the name forward. So first we'll go through our introduction. We'll get into some background on chain of thought reasoning and talk about some attempts to do this in the latent space of the LLM. And then we'll talk about the main content of this paper and its results. So just to introduce, I think everyone around this table probably knows about it. And you know, we all know. And if you're not familiar with it, then this is just sort of a good, like very quick. LLM is a transformer model, which is going to take in token by token, and it's going to predict autoregressively the next token. So if you take the lorem ipsum, you might feed in, try to get a laser pointer here.
Bottom left.
Oh. There we go. Now you can see where my mouse is. So you feed in the token. You feed in the token low, and it's going to predict rem. You feed in rem, it's going to predict if. So all of these tokens are fed in sequentially. The transformer computes its attention to create contextual representations of each token. And finally, a softmax layer is going to give you a probability distribution over the next token. So the important thing is that these models are really just next token predictors. And as such, the question answering tasks that these models are usually used for are presented as such. You feed in a context such as, how do you roast a ham? And the response is going to be, well, first you preheat the oven, and then you do this, and then you do that. And it's going to generate this textually, one token at a time. However, more complex questions, such as Tommy ate 3 ham sandwiches daily for 6 months, and Davy ate half as many sandwiches per day for 12 months. Did Tommy eat more ham than Davy? This type of question benefits from a reasoning chain. So the reasoning chain is basically just a space where the LLM can break the question down into easier parts before answering. And now I know, folks who are involved in actual logical reasoning might come to disagree that this is reasoning at all. You know, putting the definitions aside, I call it reasoning here because in the LLM literature, when talking about the word that's associated with it in that literature is reasoning. So we'll put the philosophical discussion on definitions to discussion. So we have here the question, we have here a space where the model can generate a chain of thought to reason about or break down the question, and finally can make an answer. And in most implementations, this chain of thought is just more text, right? So the text could say something like, assuming 30 days per month, Tommy ate 30 times 3 equals 90 sandwiches per month for 6 months, which is 90 times 6 equals 540. Half of 3 is 1.5. So Davy ate 30 times 1.5 times 12 equals 45 times 12 equals 540 sandwiches. Thus, they both ate the same number of ham sandwiches. So the answer would be no. So it's much easier for the LLM to say no after that, going through those steps, as opposed to after just seeing the question in the context. So the question that this paper comes along to ask is this optimal, that we're generating all of this, the intermediate steps as text? And the question can be further refined to, well, reasoning be done in the latent space of the model. So instead of actually generating the text, we're going to generate some arbitrary sequence of maybe not even tokens, which is going to internally transform the state of the model in a similar way as that much longer. So comparing the two paradigms, we have text reasoning chains, of course, human readable, while latent reasoning chains are not. Text reasoning chains are restricted to only exploring one possible reasoning path at a time, whereas a latent reasoning process would be able to explore multiple parallel paths simultaneously. Text reasoning chain is inefficient because it requires many tokens, and whereas a latent reasoning chain can require very few tokens, maybe even less than 10.
Are they defining latent? Is that a term of art? Is that something that?
It's it's explored in prior work. We'll get to that. So most of the tokens that are in this textual reasoning chain are only there for fluency, sort of to glue the syntactic structure of the text together, and don't hold critical information that's necessary for the LLM to achieve its answer. Whereas a latent reasoning chain would not be bound by linguistic fluency. And finally, the final answer may not adhere to the generated reasoning chain. It could go through these steps and then finally decide, well, we're just going to go and output something else anyway. And this has been explored by multiple works. Whereas with a latent reasoning chain, that might still happen, except it really doesn't matter, since you're not generating anything that should arguably be consistent with the answer. It's just some additional scratch space for the model to do transformations. And this is arguably, and this last point is sort of my own extrapolation here. It's arguably closer to what humans do, in that we think with mental abstractions and imagery before speaking, rather than actually verbalize our own internal thoughts out loud every time we plan before we speak. So we're going to just quickly go through some background on the literature for chain of thought reasoning. So the term chain of thought, or COT, which I think I'll use for the rest of this presentation just for brevity, is originating in the work of Jason Wei et al. And the paper was called Chain of Thought Prompting Elicits Reasoning in Large Language Models. However, COT is now widely used in the literature just to refer to any reasoning chain of any structure, not necessarily the one explored by Jason Wei in 2022. So guided by this wonderful survey, we're just going to go and look at a number of the most popular ones. You've looked at LLM engineering guides. You've probably seen some of these. So the first is the concept of a scratch pad. This was explored in 2021, where given some mathematical problem, rather than directly trying to generate the answer, the LLM would generate a scratch pad where it could then go and do intermediate steps, kind of like what we were just showing before. This particular work, they specifically trained or fine-tuned, meaning gradient updates to the weights, the model to perform this task, which is not typically what's done anymore. So this is why literature doesn't usually refer to this particular work as chain of thought, but it's there sort of as the origins of the idea that given more space to think, LLMs do better jobs. So coming into Jason Wei's work, I don't know if you can really see this. Okay. So you have the model input. In this case, there's a one-shot example. So there's a question and answer followed by another question, and then the model's got to give the answer. But the question is a mathematical reasoning problem. The answer is elicited immediately after the question, and the answer, and of course the model is going to get it wrong. But now, it's going to be now. If the model is prompted in its example to rather than just give the answer, but to break the answer down into steps, then it will follow that example and it will break the test answer down into steps and come up with the correct answer. And this is what was coined as chain of thought prompting by Wei and colleagues in 2022. Almost immediately following that up was zero shot COT. There we go, that's much easier. So zero shot COT basically compares, okay, well, we can do chain of thought. We can do, first of all, few shot prompting, which we know doesn't work to directly output the answer. Oh my God. What do I, there we go. Zero shot prompting, so just ask the question and get some answer out. We can do few shot chain of thought, which is what we just saw previously. And now we can do zero shot chain of thought. So all you have to do is add let's think step by step after your prompt, and magic. The LLM will break the problem down and get a much better answer. And they showed dramatically increased zero shot results, something on the order of, I don't want to put the results in the slides, but it was something on the order of the difference between 18% and 80% on a test set of math problems, just by adding this incantation into the prompt.
Clarify, the paper was about this line. That's the think by that?
Yes.
That was a publication.
That was the publication.
Damn.
We usually use one of the examples in the paper that led to us putting chain of thought into ChatBS was explain step by step. You tag it, the same thing.
Yeah. I mean, nowadays the models are smart enough to know what you want, but back then they were experimenting with the original GPT-3, which was at the time
Stones and knives.
At the time, GPT-3 and one of Google's largest monster models were the only two capable of doing this. And that was just 3 years ago. Okay, so then we have a follow-up paper called Self-Ask. So here again, they're comparing, well, if you just pose the question and try to get a direct answer, then you don't get a good result out. But if you could do chain of thought, if you do chain of thought, you still might not get the correct answer out. In this case, they're asking who was president of the US when superconductivity was discovered. So I guess it requires discovering A, who was president, or what year was superconductivity discovered, and then B, who was president during that year. So it first does that first step, and then it comes up with a hallucination of what the second step would be. So the updated approach here was then to prompt the model explicitly to come up with a list of follow-up questions in a specific sort of Q&A format. That's why they call it self-ask. And the model is able to do better with this more structured chain of thought that's tailored to breaking the question down into specific sub-questions. Then we have self-consistency. Self-consistency, as usual, compares itself against standard chain of thought. So you have prompt, it does the chain of thought, it gets the answer. Self-consistency will repeat this multiple times, sampling a range of different reasoning chains, and then marginalize out those reasoning chains to see which of the final answers is most common across the different reasoning chains. So if you get to the answer is $18 twice and the answer is $26 once, then $18 wins because it's more probable. So it's asking the model to do a lot of reasoning and then saying, okay, what is the most consistent result? Then you have
how a quantum computer works. You do it 1,000 times.
So now we have program-aided language. So as usual, comparing against standard chain of thought. But they found that if you prompt the model to break it down as code, so for each piece of the answer, you're going to write a line of code that's going to define a variable and set it to a value that corresponds to what's in the answer, then the model will eventually write a line of code at the end that will produce the answer. So it doesn't actually, the model doesn't actually have to do the math. It just has to come up with a way to tell the computer how to do the math based on the question. And then you can run it in a Python terminal and get the answer. That's a pretty clever approach. And this is, I've seen others like this, but this was 2 years ago. Even just going further, we have least to most prompting. So least to most prompting is about problem decomposition. Least to most prompting will take a problem. Here it takes Amy 4 minutes to climb to the top of a slide. It takes her 1 minute to slide down. The water slide closes in 15 minutes. How many times can she slide the slide before it closes? So the language model is prompted in stages. First stage is to come up with questions that we need to answer before we can answer the main question. So to solve how many times does she slide before it closes, we first need to solve how long does the trip take. So then they prompt the model to, with that secondary question, it then is able to do a standard chain of thought to come up with the answer. And then the second stage, the third stage here, is to take that intermediate answer, append it to the context we had before, and then try to approach the main question with that intermediate answer already having been given.
How did it know to even pull that out? That origin question there.
The trip.
You mean how
did it know to even do that?
I guess based on the way they prompted it, they would have to.
So what we're not seeing here is sort of the setup, the extra context to deconstruct it like that.
Yeah, like where does it get the word trip?
This is all well, it's going to be prompted to do this task. It's basically to look at a complex question and come up with a list of prerequisite questions.
Okay.
What we're not seeing here is if they had few shot examples demonstrating the model how to do that, then they're not showing us those few shot examples here on the slide. Now we have a comparison of chain of thought, self-consistency, and tree of thoughts. Tree of life, right? So we have first standard input-output prompting. We have input followed by a chain of thought. That's chain of thought prompting. Now we have self-consistency. You sample a bunch of chains and pick the majority vote. Now we have tree of thoughts, which sort of breaks this down as you have a bunch of diverse possible reasoning chains, but we're going to try to do a tree search to traverse which of the steps in those chains is more probable than others, to kind of try to come up with the shortest path between the input and the output. So that's yet another prompt engineering technique that attempts to do this type of reasoning chain to improve LLMs. Now, these reasoning chains have been integrated into larger frameworks, such as agentic frameworks where you put reasoning in a loop and basically get the LLM to iteratively improve itself or to attack larger problems. Self-refine is one of those. Self-refine puts the model in a loop where it first generates an answer, then prompts itself to get feedback on that answer, and then refines its own question, and then does that several times before it's satisfied. For example, in a dialogue context, the user says, "I'm interested in playing table tennis." The response is, "I'm sure it's a great way to socialize, stay active." The model will ask itself for feedback on that, and whether or not the response was engaging enough, or whether the user would understand it. So it says, "Oh, well, you didn't provide information on table tennis or how to play it," and the user will lack understanding of the and the response shows lacking of understanding of the user's needs and state of mind. So then it will refine it and rewrite the response given the feedback as, "This is great to hear. It's a fun sport requiring quick reflexes, good hand-eye coordination, etc." So chain of thought is being now put into a loop to create systems. So on chain of thought, I could probably have prepared a 3-hour presentation just on that, but that's not what we came here to talk about. So latent COT tries to take this approach of generating textual reasoning chains and compress it down into the latent space of the model for the benefits that we just enumerated before. It's more efficient, you can explore multiple reasoning chains simultaneously, etc. So the first attempt to do this, and the ones who defined this problem of latent COT, was Deng et al. In their 2 publications in 2023 and 2024. They introduced what they call implicit COT, or ICOT. And the approach is to try to rewrite the latent representation of the question so that it reflects what you would get at the end of the chain of thought. So here we have standard no COT, right? You have 12 times 3 equals, and then the model will go through transformer layers, and then it will get the answer 36. And they can, you can look at this in terms of random variables. You feed in X and you get out Y. No random, well, there's no latent random variable there. Here, explicit COT is going to do sequence generation. It's going to generate 12 times 3 equals 6 plus 30 equals 36. So the 6 plus 30 equals intermediate piece here. Intermediate piece here is representing a latent variable Z, which is going to contain the information needed to prompt or to condition the model to generate the right answer. So implicit COT takes or attempts to compress this latent variable Z into the transformations that happens as information moves up the layers of the transformer, cutting out the need to do autoregressive steps to get there. The goal is to keep the accuracy boost without explicitly generating the reasoning chain. I included this just in case somebody has the slide deck later and wants to read it. Yep.
Which model did they use it on?
This one?
The previous one. This one.
There's a small open source model. I forget exactly which one. It was either the original GPT-2 or maybe one of the Llama models. So what they did is there was a 3-step training strategy. First is to take a teacher, which is a LLM that has an explicit textual train of thought. Take the intermediate hidden states at each layer that correspond to each of these tokens. Each subsequent token, you take it from the next layer so that it has the ability to attend to the previous layer. And then extract them and substitute them as for the latent states of the final token of the answer that you get in the student model that does not use explicit textual COT. So here, 12 times 3 equals 6 plus 30 equals something. Here, this is just 12 times 3 equals something. And we want the latent representation of equals to match the latent representation of 6 plus 30. An additional objective is then to use the latent representation that's computed from 12 times 3 to be able to predict the internal latents that you get from your teacher model. They call that an emulator. Honestly, I'm not sure exactly why they needed to do that, but that's what they did. And then finally, they put the two together. So they have the emulator model generate the hidden states from equals, and then they, if you recall from the first step, the student model is trained to use those hidden states to predict the answer. The second stage trains it to predict the hidden states from the latents of equals. And then the third step sort of puts it together. So it's going to implicitly compute the latent states of the reasoning chain and then convert that back to a prediction of the answer. So it's sort of an onerous training process because you have to go through those three stages and you need a student and a teacher model. However, the authors realized that they actually didn't need to do all of that. Instead, all they had to do was split the training up into stages, where each stage they incrementally remove part of the textual reasoning chain until at the last stage there is nothing left. So if you take, let's say 21 times 43 equals 84 plus 63 equals 804. And then at the second stage, you remove the 8, then you remove the 4, then the plus, then the 0, then the 6, then the 3. Basically, what this does is at each stage, it incrementally updates the representation of this equal sign to be able to predict stages of the reasoning process that are further and further along until it can eventually predict the answer that would have been output from the reasoning process. And they found that this works even better. It outperforms the three-step knowledge distillation approach that they originally used. This is the results that they had. I guess just the important piece is to compare these two, ICOT-KD, the knowledge distillation three-stage approach, with ICOT-SI, which is the approach where they incrementally remove tokens. And you can see that in all of these different tasks, the incremental removal of tokens outperforms the knowledge distillation approach. And all of these also are outperforming baselines that are either using no or explicit COT, even using GPT-2 small, comparing against GPT-4, which is pretty crazy.
Yeah, that's pretty crazy.
Not surprising though, because they're deliberately training this on this task where GPT-4 is just left to its general devices.
So it's kind of a baseline in a way.
Yeah. This was the results on the grade school math problems. They found that explicit COT actually does better than all of these methods, except the implicit COT methods do a lot better than not using COT at all. A second approach was pause tokens. Pause tokens was this from Goyal et al. In 2024. Pause tokens basically just introduce some scratch space in the middle of the sequence here. So 5 squared plus 4 is 25 plus 4 is, right? So here it was a 5 plus squared plus 4 equals, and then pause, pause, pause. These are learnable tokens, which means the LLM can update the parameters of those tokens as it trains. And then it will just continue on where it left off. The idea being that additional computation and transformations can happen in the attention mechanism in this space, which would presumably encapsulate parts of the reasoning chain. And the goal is to provide space for the LLM to think without needing to output text tokens. This is kind of analogous if you're a computer vision person. It's analogous to the registers that are used by the Dino V2 model. Dino V2 contains these disposable registers here, whereas the pause token model contains these disposable pause tokens here, and they're ignored in the output in both cases. So just a nice visual representation of the effect that this has in a vision transformer is that each one of those disposable registers is attending to different parts of the image. So if you have the coffee cup with sugar, one of those registers is attending to the liquid, one is attending to the spoon, one is attending to the sugar, one is attending to the outline of the cup, and the classification token, which aggregates all of those, is able to take a summary of all of those different individual pieces that the register tokens were able to attend to. So it has the opportunity to sort of summarize what's in the image before going ahead and outputting to the classification head. And the same concept would apply here. Pause tokens would allow the model to do some summarization over the context before it continues to move forward into the answering process. So this brings us to chain of continuous thought, or coconut. Here, coconut is, again, comparing against standard chain of thought, where you autoregressively go and say, here's my question, generate the reasoning chain step or token by token, and then finally generate the answer. No, instead, we'll get the question, put in a begin thought token, and then basically take the output latent of the LLM, which is the last hidden state before the softmax, and feed it directly into the token embedding of the next position. So think about that. There's no tokens used in between these spaces. It's literally just taking the output of the hidden state of the LLM transformer block, the top one, and feeding it directly in as if it was a token. So this is truly a continuous thought because it never actually leaves the vector space that the LLM uses internally. It's not detokenized and converted back into the discrete vocabulary space. So our latent ipsum example, basically saying, well, what would happen if we tried to use this technique to model the lorem ipsum? You might pass in your lorem here, and then it'll do some internal thinking, generate this latent representation, feed it back in here, generate another one, feed it back in here, and then it might generate the last token of the lorem ipsum. And if you try to interrogate what one of those tokens in the middle actually would output from the language modeling head, you might get something that's unrecognizable. Although there is a method that can be used to probe the latent reasoning chain, as we'll see soon. So the way that this model is trained is in stages, just like ICOT. So the original linguistic chain of thought data includes question, step 1, step 2, step 3, step n, followed by the answer. The first stage is just to insert the begin and end tokens here. So it doesn't really do anything, it just inserts these tokens and continues to generate step 1, step 2, step 3, step n answer in text. The loss is the cross entropy loss. It's computed, standard language modeling loss is computed on everything that comes after the EOT token. So all of these reasoning steps followed by the answer, but not applied to the question or the reasoning steps. The first stage is then to take the first reasoning step and replace it with a continuous thought. So begin thought, one continuous thought, end thought, then step 2, step 3, step n answer. The next stage pulls out another text reasoning step and introduces another continuous thought. And then it does that until stage n. And by stage n, we replaced all of the remaining textual reasoning steps, and we have the question, begin thought, continuous, 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 end thought, answer. So we've completely eliminated the textual reasoning chain. Yes.
So as an innocent, how do you generate training data for this type of models? I mean, it can't be just web scraping or something, right? It has to be pre-composed libraries.
The training data would come from a data set where the chain of thought for one of these question answer pairs has already been written out.
Yeah, exactly. Yeah. So how big are these databases? Do they need to be handwritten?
No, they already exist. I mean,
Innocent.
each one only has somewhere between several thousand to tens of thousands of examples.
That's not much.
Yeah, because they're fine tuning the existing pre-trained model to do this.
So are they training or fine tuning?
They're fine tuning.
Fine tuning. Okay, because you're talking about training, right? So that was.
Yeah. Well, I guess they say training procedure, but what they're doing is they're starting with a pre-trained model. And
okay, that makes a lot of sense. Yes, because yeah.
So
there's also a question in the chat, by the way.
let me look at the chat. How will the model perform in a complex environment where different COT strategies may be needed for different problems? So they evaluate this on the grade school math data set, and they also evaluate it on a tree-based logical reasoning problem. So I guess it would just have to be fine-tuned on the target domain, just like we usually would, except instead of using discrete chains of thought, we would be able to use these latent chains or continuous chains of thought for more efficient reasoning at inference time. But ultimately, you would still need data in their target domain and textual chains of thought in your data set in order to go through this training process.
So when I asked the question, not sure if you can actually hear.
Yeah, I can hear you.
Oh, I was thinking the original very first version chain of thoughts was actually zero shot, which allows the model to sort of be given different strategies for different problems. Now, once it's nicely trained, it's like someone learned a bad habit, if that habit happened to be bad. Now, if we wanted to learn a different habit, you have to sort of like wash out the old learned content, especially for the tokens, the last algorithm where you add in additional tokens and directly take the output logic to put them back as input token. I was just like, it must be hard for them to learn something new after this.
Yeah, the authors actually discussed this a little bit. So as you said, the original chain of thought, zero shot chain of thought, was emergent from pre-training, right? But here they're focusing on fine tuning on specific data sets that already have chains of thought written out for them. But they talk about the potential to do to incorporate these continuous thoughts in the pre-training process, which was beyond the scope of this paper. But if it would be done that way at a sufficient scale, then we would expect some type of zero-shot chain of thought capability using continuous thoughts, analogous to what we see with COT. So this is sort of like, put off to future work, but recognized by the authors. All right. So at inference time, what happens is, right, just like we discussed, we put in the question, we put in the begin thought token, we generate autoregressively these continuous thoughts, no tokens. Remember, we're just taking latent output and feeding it back into the next position's input. And then they'll generate a fixed number of these, like maybe 3 of them or 4 of them, and then input the end of thought token to condition the answer. So the main results were found by evaluating on 3 data sets. One was the GSM8K data set, grade school math word problems, kind of like the ones we were looking at. Pronto QA, which is a logical reasoning task on a tree-structured ontology of fictional concepts. So we'll look at what that means in a minute. And Pros QA, which is a data set that these authors also contributed. It's a harder version of Pronto QA, which requires more complex search to find the correct path through that tree-structured ontology. So GSM8K, this is an example of what you find in here. Your standard grade school math word problem. My 8-year-old daughter is probably working on one of these as we speak. Pronto QA. So here you have a question which introduces a knowledge graph of fictional concepts linguistically. So you have something like brimpuses are not luminous, shumpuses are amenable. Each yumpus is a loris. Gorpuses are shumpuses. Each zumpus is a grimpus. Grimpuses are rompuses and dumpuses are not floral, etc., 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 etc. Finally, Stella is a brimpus and Stella is a zumpus. True or false? Stella is not floral. So it's going to have to use these rules in its chain of thought in order to decide whether or not Stella is floral. So the answer would be Stella is a zumpus, zumpuses are gorpuses, Stella is a gorpus, gorpuses are rompuses, Stella's a rompus, rompuses are yumpuses, so Stella's a yumpus, each yumpus is a lorpus, so Stella is a lorpus, and thus, or every lorpus is floral, thus Stella is.
That is proper.
Yeah. Prose QA, they deliberately reshape the structure of the questions and of course the assertions. So here, every assertion here is basically A is a B type of assertion. So every shumpus is a rempus, every shumpus is a yimpus, every tempus, every terpus is a gurpus, every gurpus is a brimpus, Alex is a rempus, etc., etc., etc. And the question is Tom a lempus or a scrumpus? So it has to decide, which of these paths are we going to explore in order to figure out whether or not Tom is a lempus or a scrumpus, given the knowledge somewhere in here that Tom is a terpus. So it's a 3-step chain. Tom is a terpus, every terpus is a brimpus, and every brimpus is a lempus. Thus, Tom is a lempus.
Do they go into being able to figure out contradictions? Because in the previous one, you had not. So you could have gotten you're floral and you're not floral.
I don't think in prose QA, I don't think they have any contradictions or any negations at all. But what they say is that there are many different paths, longer paths that you can go down before you hit a dead end than there were in the original Pronto QA dataset.
What could be a contradiction? Because you could have a scrumpus is orange and a scrumpus is green.
But the previous one, something is not floral and something is floral. This one didn't have any negations, but this one had a negation. Yeah, there. Every rumpus or whatever that dumpuses are not floral. And then someplace else, something is floral. So, you could get to a path.
But I guess the thing so Stella is a brimpus, Stella is a zumpus. Depending upon how that categorization of Stellas is a brimpus and a zumpus from the same class? Are they exclusive or not?
Well, they don't state that, but
I know, but could you
negation is-
include that? Could you say, could you have a brimpus can't be a zumpus?
You could, and then you wonder how it would work.
We've been sitting here for a long time.
I mean, these are the kinds of things that mess with reasoners.
Well, but this is, I guess what I was going to say is that a different point is two things. One, if you had a knowledge graph that had that information in it, if you could define in your ontology that, okay? But the question relevant to this is how would you get that sort of knowledge? How would you teach it to reason in that same way? So it could detect that exclusivity. You can't have a grumpus and a wumpus, that's the same classification.
Yeah. So in this, they sort of skate around that problem by not actually using negations and the types of examples.
Disjointness, yeah. Right.
Rather, they focus on the depth of the planning or the depth of graph traversal that's needed in order to get to the answer, with the motivation that with traditional chain of thought, you can only explore one of those paths at once. This continuous chain of thought, you can explore sort of a breadth search, and you can explore multiple paths simultaneously.
But I guess the big point, and you're kind of getting at it, is the kind of reasoning we're talking about is not usually found in chain of thought reasoning.
Right.
Period. It's
Right.
not, it's just, what is the problem with chain of thought reasoning? It doesn't.
Right, it's basically forward chaining, but the fact that one example had not made me. oh, this could be cool.
They don't talk about negations at all in the paper, but I think that's a great point. And when we look at the results, I suppose if we were to do an analysis on where it got wrong, I bet you would find stuff like that. Okay, so
Really quick question, if you don't mind. Do they test any questions that involve like asking if like two entities are premises or premises? Or do they only ever test questions where they ask if only one entity is one of those things or not?
I didn't look at the data, so I don't know, but the examples in the paper show a question about one entity,
Right.
with the graph being populated with information about multiple.
Okay.
But it is possible, I just didn't look. So anyway, this is an example graph that you can create. So we have Alex. Alex is sitting here, and Alex is a Grimpus. And we want to know whether Alex is a Gorpus or a Bompus. So the correct path through here would be Alex is a Grimpus, and a Grimpus is a Gorpus, and thus a Gorpus is a Bompus. Thus, Alex is a Bompus. So because we can't get from Alex to Gorpus in this graph, there's no edge, there's no directed edge that will let you take that path. So there's many opportunities for the reasoning chain to hit a dead end, and if you're doing standard chain of thought, you might have to backtrack, and it'll be very inefficient. There's 23 nodes in each of these graphs, 36 edges. The length of the shortest path is on average 3.8, and the number of shortest paths on average 1.6. So here's the results that they came up with. And the baselines are all ones we've talked about. We talked about ICOT and we talked about pause tokens. So they found that for 8th grade math problems, or grade school math problems, Coconut outperforms ICOT, and it outperforms no COT, outperforms pause tokens, does not outperform standard COT. Because grade school math does not require a lot of branching and planning. It's just more, numeric comprehension type stuff. Pronto QA, Coconut, COT, and pretty much all of the baselines except for pause token do equally well. And the authors figure that the Pronto QA was too easy of a data set just because it didn't give enough of an opportunity to get lost in that graph. But in Pros QA, they found that non-COT and textual COT achieved pretty much the same performance, whereas ICOT and Coconut both achieved almost 100%. So this is a clear evidence that when you have a case where you have to do a lot of upfront uncertain planning and traversal of a graph of possible paths, the latent or continuous chain of thought is superior to standard text chain of thought. So the conclusions that they have is, like I just said, in planning intensive tasks, we have much better results with latent approaches. They found that the LLM will still need guidance from text COT to learn how to do this in the latent space. They had an ablation where they basically did not do the multi-stage curriculum and just replaced the chain outright with the continuous thoughts, and they got poor results on that. They found that the reasoning chain is able to do parallel reasoning paths in the latent space. So what they did is they used the language modeling head to probe one of the latent thoughts, and they found that the most likely tokens coming out of that probe were 9 and 180 when the problem was 3 times 3 times 60 equals what? So it's either 9 times 60 equals 540 or 3 times 180 equals 540. So 9 and 180 represent intermediate variables of two alternate reasoning paths to get to the answer. And the latent thought here contained information that pointed to both of those paths. And also, chaining these continuous thoughts will enhance reasoning, as they showed by showing what happens if you gradually increase the number of thoughts that you use per per textual step during training, they get higher accuracy. So we're almost out of time here. So
It's okay.
we have 5 minutes.
We started late too.
So we're up in the last section, so if we get through on time. So the authors, for their analysis, they want to understand, well, what's actually going on here when this model is learning this method to do continuous chain of thought in the latent space. What is actually happening here? What is the model learning? So they trained a special version of Coconut where they, at each stage of training, they're going to mix the current stage with 30% of examples from the previous stage. So the effect of that is it doesn't forget how to use smaller numbers of continuous thoughts. It continually learns how to use more and more continuous thoughts, but then is also capable of being prompted with the EOT token to shift back to the textual reasoning modality at any time. And what they do, they use this case study and they tried a bunch of different things on it. First, they tried standard chain of thought, which had this error here. Alex is a lempus, a lempus is a scrumpus. I don't have my laser. Where's my laser? There's my laser. Alex is a lempus, lempus is a scrumpus, a yumpus is a rempus. So it sort of jumped on a non-existing edge somewhere else on the graph. I don't know where yumpuses are, but it sort of jumped here. It hallucinated an edge that doesn't exist, and then came to the conclusion that Alex is a gorpus, which is clearly incorrect. Coconut with only one latent thought also went that route. Every lempus is a scrumpus. Every scrumpus is a brimpus. And now it hit a dead end. So it just output Alex is a brimpus because we're at a dead end, which is what they classify as a wrong target type of error. If they add a second continuous thought, then it's able to go, Alex is each rorpus is a bompus. So it sort of skips, the latent thoughts carry it over here into this area, and then it just completes every rorpus is a bompus, thus Alex is a bompus. So what they found is that as they increase the number of thoughts that they're using from 0 to 6, the number of instances of those errors, of wrong targets, longer than the shortest optimal paths, hallucinated edges, and incorrect labels in the case where you have no textual steps left and you go directly to the answer. The more latent thoughts you use, the more it gets the correct label immediately and does not exhibit those types of errors more frequently. And the way it's actually doing that is the following. So if we break this down further, and remember you have these two cases where you either have only one or two latent steps. So what Coconut is actually learning under the hood is it's implementing a latent breadth search, first search, or BFS search on the tree of possible reasoning paths. Each thought is representing a level of depth in the BFS search. So the first thought represents all of these options here in the first step away from Alex.
Sorry, I got a 5 o'clock.
The second thought then expands this breadth first to consider all of the nodes that are neighbors of level 1 nodes here. And it assigns an implicit value function, basically a learned estimate of how likely the next node is from the current level to the correct answer. And the numbers that you see here, these numbers are estimates of the implicit value function that is assigned to each of those nodes in the latent reasoning process. And the way they're able to estimate that is by taking the latent reasoning process at this stage and forcing it to decode the rest of the reasoning process in text and looking at the probabilities given by the language modeling head for all of these possibilities. So if you generate one thought and then say, what is the probability that the next token is going to be stirpus versus lumpus versus zorpus versus grimpus, you find that there's an equally likely probability, maybe slightly higher for lumpus than grimpus. But if you then go and generate a second thought and evaluate the probabilities of all of these neighbors that could either come from moving to Stirpus or moving to Lempus or to Zorpus or Grimpus, you find that only those that come from moving to Grimpus yield a high probability. The rest yield probabilities are very close to 0. So what's happening is at k equals 1, the thought at the thought where k equals only 1, choosing the Lempus path is more likely than choosing the Grimpus path. However, at k equals 2, the continuations from that would come from choosing Lempus become improbable. They're sort of pruned out. And what happened is Coconut sort of deferred the hard choice of picking between Lempus and Grimpus at k equals 1, carrying information about both of those choices forward in the continuous thought. But then at step 2, at k equals 2, it will be able to figure out, since these nodes are now closer to the edge of the tree, that these up here are irrelevant, while these down here are likely to yield the correct answer. So this is a general pattern. There's a parallel reasoning chain happening. Multiple different paths are considered, and then as we go forward, the subsequent thoughts allow information to be pruned out of the representation of the continuous thought, while the correct path is amplified, which they show here. They're picking at the point of the first thought, nodes that are higher up in the tree are going to maintain higher probabilities, but at the second thought, those nodes are going to become less and less probable as the model is able to disambiguate what the correct path is. In traditional COT, that would require expensive generation and backtracking one path at a time. So that brings us to the end. Just 2 discussion questions that I came up with. One is that training with these types of continuous thoughts is inefficient. It would require on-the-fly autoregressive steps with each training example, because unlike token embeddings, these values here are conditioned on past outputs. So they can't be input in parallel to the model, like a single forward pass, the way you typically train an LLM. And you can't pre-generate them, cache them on disk, and then feed them in parallel, because distribution shifts would happen in the outputs here after every gradient step. So it sort of forces you to generate while training, which is very inefficient. My second thought here is this could potentially be applicable to other modalities, like, for example, world modeling in video. If you want to predict what will happen later on in a video without rolling out and playing out every frame, then you could potentially use something like this. Similarly, spoken dialogue. If you have a model that's generating spoken dialogue, then maybe you could use latent tokens or latent thoughts to represent the planning of what you want to say without actually putting a full text translation of the speech in the context. Those are my thoughts about challenges and potential applications of this approach. And that brings us to the end, so we can open it up for discussion.
Nice. And I have a thought first. I think that potentially, if this could be applicable to something like logistical planning of sequence of events or moves under some condition of certainty, which obviously previous move somehow conditions what the next thing is, and then each time you make the next decision and so forth. There is a program from Air Force that asks for something like that. So, of course, this is language, but we're talking about moving equipment or troops or planes or whatever in some sequence in order to get something delivered to a particular place or so. So I wonder if that could be used for planning most efficient path, given whatever you have at your disposal to reach some particular objective.
I suppose so. I mean, the main benefit of this approach over train of thought, if you're using an LLM that is for planning, and a lot of times you could argue that if you have the right problem set up for a traditional planner that would give you deterministic results, you would want to use an LLM. But if you're using an LLM for planning, this approach has the primary benefit of allowing you to plan more efficiently rather than, having to recurse through depth first search of textual chain of thought. So I don't know if it will do it better, but it will definitely do it more efficiently.
Yeah, that's one of the, I think, parameters is if you can do this more efficiently. And,
Yeah. Elkin.
Yeah, so I have two questions. The first one is, do they mention when to stop thinking? Because 3 is the correct number for this problem, but what about other problems that might need more steps? Do they have any idea of when to stop?
They don't have a general formula at when to stop. And of course, because they're fine-tuning the model rather than pre-training the model with continuous thoughts, they only know how it performs on these problems, like May's question earlier. But they did talk about exploring 2 possible ways of determining when to stop for these tasks. The first was to just use a fixed number of thoughts, like they ultimately went with. And the second was to add a logistic regression style head top of the model that would predict 0 or 1, basically continue or stop. And so that way they could have a dynamic number of thoughts. And they found that on these tasks, it didn't matter. The performance was about the same either way. But I don't think that would generalize to all tasks. I think they would have to try more than just 2 types of tasks to really get a sense for what would be a good general stopping condition.
Okay, I actually have yet another question. 3 in total. Okay, so
We also have someone with their hand up here in the chat, so.
okay. Do you want to go for them first?
Yeah, sure. Erfan, go ahead.
Hello, can you hear me?
Yep.
Okay, I had a quick question regarding the relationship between the steps that are in COT and the number of thought steps. So if we could go back to the figure.
Is this one?
Yeah, I guess maybe a couple of slides earlier.
I think you had like a table.
With the green ones.
Oh.
Yeah,
yeah.
the results table.
This?
Yeah, I guess K here is the number of thoughts, and then 1 slide before. 1 slide before. I think it was the results table.
The table, okay.
Yeah.
That's quite a few slides back. Here we are.
Okay, my apologies. My memory is bad. Okay, so here the number of tokens corresponds to the number of steps, or I guess what are the number of tokens here?
Number of tokens here would be the number of autoregressive steps needed. In the case of Coconut, they're not really tokens, but they basically count them as if they were tokens because they have to perform a forward pass and with an autoregressive step in order to do it. So 9 tokens would be you've done 9 forward passes, whereas in COT they did 92 forward passes because they needed to generate 92 tokens.
Got it. Okay, that makes sense. Okay, so here they try to compress, I guess, each COT step into 1 forward pass is essentially what they're doing. And
yeah, one or two, it's variable. They try different one for different task.
Oh, I see. Interesting. Okay, but they've only tried it the same way implicit COT did, right? Where they take out 1 step and replace it with a thought step in sequential order.
So implicit COT did it 1 token at a time rather than 1 full reasoning step at a time. I guess what they would consider a reasoning step wasn't exactly defined. I assume it meant sentence, but they did it with more of a block of text where a full sentence of the reasoning chain would be removed at a time, whereas ICOT did it token by token.
Oh, I see. Okay. I guess perhaps step is defined given the data sets that they're using.
Maybe, yeah.
So did they try to just like do it in reverse order? So if they take step 1 and replace it with a thought forward pass, but keep step 2, 3, 4 until however many, and then you get the answer. But did they try to like just do like one step or 1 and 2 thought steps and then just skip straight up to the final reasoning step and then the answer? I guess the question that I'm implying to ask here is the model learning to model like the COT steps in its latent space as a byproduct of this training setup? Or is it like, is this the most efficient way? Like, why can't the model perform multiple steps or even all the reasoning steps on just one inference forward pass? Like, it's learning to mimic human reasoning or human reasoning steps, but it's a machine. It can perhaps work differently.
Yeah, so 2 thoughts here. So the first thing is whether or not they could directly skip to the end. So they would go thought 1, thought 2, and then skip like to reasoning step 9. No, as far as I know, they didn't try that. So yeah, no, I can't remember them talking about that. The different ablations that they did is here. One was without curriculum, where they don't use the text chain at all. They just say replace it directly with all of the thoughts all at once and train it as a single stage. Without thought, they essentially do the same thing as ICOT. They go directly from the question to the answer and incrementally remove the steps, the reasoning steps as they go in each stage. And pause as thought is they're using the pause token instead of using the continuous output. Those are the only ablations that they ran. And the second thing was, well, why can't you just do it in one step? So I think that it depends on how it's trained. So if they're training each thought or a group of thoughts to correspond to a single reasoning step, then you have still have that grid search problem where after each particular continuous thought, the model has only traversed as far as it would have with a partial reasoning chain. If the training objective would always only output a single continuous thought, and that single continuous thought is responsible for taking the place of the entire reasoning chain, you could argue that maybe it would learn to do that, but I would expect that you would need a much larger, model in terms of the parameters, or even just the raw vector size that you're using for your hidden state to cram all of that information in. So the model they used actually for their experiments is GPT-2.
Yeah, that's fair.
Kind of surprising. So
and Phi 3.8, right?
What's that?
And Phi 3.8.
No, they didn't use Phi. They just used GPT-2, which is
I was
really surprised that people are even still experimenting with that now.
Yeah. Okay. I would be interested in seeing if Phi does better, but yeah, I guess a follow-up remark here is that like using the latent space to reason is definitely like an interesting idea. It obviously it's more efficient because you don't have to do as many forward passes as if you're doing traditional COT. It's like 9 to 92, right, for Pronto QA. But I wonder like I wonder like if the models, the bigger they get, the less thinking they need to do. So the less forward passes they need to do. Okay, that was my last remark.
Yeah, I think you'd find in general, yes, because the larger the models are in the parameter space, we know that they can memorize a lot of stuff really well. So if you're just using benchmarks like this, like GSMPK, then if the model can squeeze more into its memory, then yeah, it's going to do better in all of the settings. So I think it would be hard to ultimately disentangle better performance due to just sheer memorization due to larger parameter capacity versus actual benefit of using implicit COT. But if all the experiments are done using the same model size, then you've control for that variable.
It's a possible a hypothesis on why they went with the dusty old GPT-2. Could that be because also because the more recent models, they've been mucking around with them to, they're messy models when it comes to simulating reasoning, whereas GPT-2 is a cleaner model from that perspective.
It could be, yeah. I mean,
because there's no way it's like, and don't do your own reasoning.
Kind of modern models have also seen a boatload of data in pre-training, including many data sets that have been created and are out there on the internet that may already condition it to do well on COT style tasks. So
yeah, I'm in some experiments that we did in Kristen's class like a year ago or so. There was evidence that there was, they had trained on certain things that we were trying to. So we got unreasonable results when we shouldn't have got them.
Yeah, I'm surprised.
My question would have been if we're now entering a new era of DeepSeek research where everybody jumps on this model since it's open source, but actually it's a good counter argument against it.
I wasn't actually referring to DeepSeek, but
Oh, yeah.
But DeepSeek is a category of supposedly better at reasoning.
Exactly.
Okay, but the same is true of GPT-4.
Yeah, but
one GPT-4, whatever mini. These are things that supposedly have, and we don't know exactly what they're doing there.
But this is the crucial difference: is DeepSeek is open source, whereas all of the OpenAI models are closed ones. This is why I was referring to DeepSeek as a new standard, because DeepSeek allows really more transparent setup of experiments.
In theory.
In theory, yes.
In theory.
We haven't released any data yet, so. Yeah. There was a comment on the chat from May. So neither this or the original COT can deal with decisions that have branching factors. This makes me wonder how far the approach can go. So I guess I feel like the authors are claiming here that the thing that this approach is best at is decisions with branching factors. So it's interesting that you're saying that it can. Do you want to elaborate on that?
So then maybe I must meet some of the critical aspect of this. How does it deal with branching? I mean, branching in the steps sort of thing, like in chain of thoughts, you can say if.
Yeah, let me get the part where they talk about BFS. So here.
Oh, this thing. I think this is branching on the content, but not branching in the procedure. So sort of like if this is a math problem, let's do this procedure. If this is a, I don't know, second grade math problem, let's do the other procedure.
Oh, I see.
That sort of thing. That was what I had in mind. Not a criticize to this paper, was just my general reflection.
I see. So like in terms of branching out to completely different problem solving strategies, like starting maybe with mathematical reasoning and then moving to logical reasoning within the same.
Even just slightly different strategies in processing, in leading to the answer. What if I'm just trying to imagine? What if I'm getting a much more complex logical problem that I need to decide how to, like how do I work on? I remember Brown, like he used to show me the super long expression. Then you can sort of decide on which part you work on first. I may not be able to elaborate myself well. I was just trying to create a scenario where even if it's a simple problem, you may need to branch.
So what I'll say is that we've seen with DeepSeek and also with O3 Mini, which just came out this week, these models are using some kind of COT. I don't know exactly what they're using behind the scenes, but they do generate a COT in their final results, and they show it to you. And that COT has been shown to be very, very diverse, like transitioning seamlessly between code generation to planning higher level steps to doing more like social and effective style reasoning. Like if you ask them to build a game that has elements of a story inside, they'll be able to do that. So they're able to, within the same chain, and of course we don't know exactly whether it's one chain or whether they're chaining together multiple chains.
We don't know.
But these models are now starting to show such capability of branching off into different domains.
I saw that too. I read a lot of how, at least with GPT, how it does it. But we never know whether it's one model or multiple model. They could have generated that chain of thought through another separate module, not necessarily even a neural model, and then follow that with their sort of like mean trained model.
Yeah, DeepSeek is a mixture of experts too. So by definition, they actually do have multiple models, and different ones are being invoked for each token. So it's at least in that case, they are that particular assumption definitely applies, because they're different sets of parameters could be invoked that are very good at specific things.
But with the as early as GPT-4, GPT-4 0613, we were seeing if we asked it to explain step by step, give it the particular question, you do n equals 10, n equals 20, whatever, and it's coming up with different plausible chain of thoughts, chains each time. It was not, so even there was subtle differences. A lot of them were the same strategy, but slightly different, but sometimes it would go off and do something different. But it was, they were different. We're like 20 after right now, so we should kind of wrap this up.
Yeah, I think
you had your fifth question.
Okay. 21st. Okay. How do they talk about how to query the thoughts themselves? Like, gave me an answer, but how did you get to the answer?
Yeah, they did probe the thoughts by directly passing so since it's coming out of the final hidden state of the transformer, you can pass the continuous thought into the language modeling head, except since there was no loss applied during training on those positions, you might not get anything interpretable. But they did actually probe it, and they found that the most probable tokens, if you wanted to predict what would come next in the text space, did correspond to intermediate variables of their math problems. So it's not going to give you a nice human readable explanation, but it'll give you a sense of like what concepts are sitting there in that vector. And that's up to interpretation, really. It's going to be
only by the model itself, right?
Yeah, provided by the model itself.
So let's thank Abraham.
Thank you.
Thank you.
Look forward to
Thank you for joining.